So in this video we're going to be talking about velocity and perhaps how we might be able to get at the velocity given the function, velocity function. So you have in front of you, this is a this looks like an XY coordinate system, but I've labeled the horizontal axis as t, which is measured in hours, and I've labeled the vertical axis with v, which stands for velocity, and that's measured in, we'll just say feet per second. Okay? So, the main thing I want to talk about here is the relationship between the graph and the area under the graph, because that's a big concept in Calc 2, which is the class that you're in. And so if we think about this for a second, if you were just to draw a line right, if you were to just draw a line right here, I'm going sideways there. And we want to talk about what is the relationship between this area that we just colored in and the velocity curve. And so in order to understand that, we're going to go back to Algebra 1 when we talked about this. Everyone's favorite part of Algebra 1 was the word problems. And there's a whole section of word problems that were labeled sometimes some books actually call them the dirt problems or the distance, rate, time problems. So we know the distance is equal to rate times time. You may have heard that before. So distance is equal to, now rate of course is just another word for velocity times time. And that of course makes sense to us intuitively, that if you multiply how long you've been traveling by how fast you're traveling, that'll tell you how far you've traveled. And if we look at the units, if we take feet per second and we multiply that by hours, in this case, well, let's change this to seconds just so it matches up. You can see it, seconds. If we multiply this by seconds, notice the seconds cancel out and we're left with just feet. So distance would be equal to feet. And of course, any of you have ever driven anywhere, I think most of us at some point have looked down at the speedometer and see that you're going 80 miles an hour, and you think, wow, if I average this for 2 hours, I'm going to cover 160 miles. And so that's just a quick little check on total distance in relationship to time and velocity. So if you think about this, if you think about one little square here, let's take a big square out of this. If we wanted to approximate how far we've driven, we could, let me grab a different color here, we could draw a big square here. And we could say that the area of this blue square is approximately how far I've driven, because I'm taking the velocity, which is the width, multiply it by the time, and that should give me total distance, right? Because of this same formula right here. Because that's how you'd find the area of this big giant square, is velocity times time, or length times width. And of course, that wouldn't be a very good approximation, because you can see I have all this space in here. So what I'd like you to do right now is pause the video and think about how could I make this approximation better. Obviously, this is an over approximation. If I multiply this velocity times this time, what I'm doing is assuming that I was going this top velocity at the entire trip, which obviously I wasn't. So this is an over approximation. But again, stop the video and see if you can come up with a quicker way, or a better approximation for finding the total distance. Okay? All right, so welcome back. Hopefully you've come up with some ideas, and so if you've had calculus before, we know that one way to do this is to, if you think about Calc 1, when we were trying to approximate the instantaneous velocity, remember we made just small little increments and tried to get closer to the thing we're looking at. So let's use that same idea, that maybe if we, instead of looking at one big rectangle, let's look at two rectangles. So let's see, we're 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if I go 1, 2, 3, 4, 5, 6, and I draw a little rectangle right there, and then not draw this one all the way over, I'll just draw it from right there. So now what we're saying is that we could approximate the total distance traveled by finding the area of this rectangle 1 and rectangle 2. And so we're saying, if we'll use blue to match this area here, because we're multiplying velocity times time, plus this area here, because again we're multiplying velocity times time, would be approximately the total distance traveled. But again, the idea here is I'm just assuming that I was traveling at this top distance the entire time for this entire interval, and for this section I was traveling at this top distance or top velocity the entire time. And again, that would be better. And if you've again been in a calculus class before, you may know where we're going. This of course would get even better if we made even smaller rectangles. So let's say divide it up every 3 seconds. So we'll do a little line like that and draw that over. And then we're going to erase that and say, now we want that one, and then another one right here, and draw that one over, and then we'll go up there. So now the green, all the green areas, so we go like this, and like this, and like that, and like that. So if we add up all these green rectangles, the area of all these green rectangles, again, that would be approximation of the total distance traveled, because we're multiplying the velocity, which is the height of this rectangle, by the time, which is the width of this rectangle. And so velocity times time gives me distance, so that would be the distance that he traveled in this little 3-second interval. This would be the distance traveled in the third 3-second interval. This would be the distance traveled in the second 3-second interval. And this would be the distance traveled in the first 3-second interval. And again, if you add that up, you will get the total distance traveled, an approximation of the total distance traveled. Okay, and of course we can keep going and going with this. My next step would be we'll choose red this time, and I'm going to divide it up into every second. So if I draw a little rectangle like that, a little rectangle like that, rectangle right there, do another one right there, and of course I'll just keep going with these. Now notice that some of these rectangles are actually underneath the velocity curve, and some of them are over the top of the velocity curve. Whoops, sorry. So again, if we take all these little rectangles and add them up, I'm going to do a real quick coloring here. All these are just the distance they traveled in that 1-second interval based on the highest, or basically on the velocity that they ended the second with. If you add all those up, that would be a approximation of the total distance, and it would be, once again, a better approximation. How do we know it's a better approximation? Because you can see that there's less and less left over. So notice in the green rectangle, there's a whole bunch of extra stuff that shouldn't have been included. But in the 3 rectangles, red rectangles, there's just a teeny little bit that's over. And if you look at this little section, actually it's pretty close, isn't it? In this little section right here, there's very little, there's a little bit under. It's actually a little bit of an underestimation, but it's really close. So that's the idea of that we're trying to look for is this idea of breaking up the shape that we couldn't find the area of to begin with because it's just a weird shape, but we're breaking up the area into little intervals and just using a rectangular shape that we all know how to find the area of to find this total area. Okay, so I want to show you one more thing here. I'm going to erase all this stuff. What if we just take one of these rectangles and look at our options, okay? So we're going to do that same, whoops, I need a black there. Okay, let's just take this one 3-second interval down the middle. Whoops. I have options here. Actually, I think I'll use this in one because there's a more drastic change in it. So we're going to use this 3-second interval here. If I wanted to approximate that 3-second interval with just one rectangle, I have an option. I could do it the same way I did the first time, and use that area, and I'm going to use yellow for that. So this would be, this yellow that I'm coloring in right now would be the total area based on this rectangle. And you can see that there's definitely some waste, right? All this up here is not supposed to be there, but that's what happens when we're doing an approximation. Now, this is based on me assuming that he's going this in velocity the entire time. Now, what if, instead of doing that, I said, well, let's pretend that he was going the other end of this velocity here the whole time. So that would look more like this. And if we colored that in, it would just be this section down here. Now, clearly, the first one, the yellow one, is an overestimate of the total velocity. I mean, sorry, the total distance traveled, because we're using really the highest velocity that he gets for the entire section. And the second one I just drew, the one that looks green now, but I used blue, that would be an underestimation because I'm using the lowest velocity that I forgot. What I really did is I chose the velocity that he was traveling at the right end of that interval for the first one, and I chose the velocity that he was traveling at the left end of the interval for the second one. And that's something we're going to talk about later. We're going to talk about left Reimann sums and right Reimann sums. And that's the difference, is which end of the interval do I choose to draw the top of my rectangle. So now we know that the actual total distance that I'm looking for, and I'll color in with this kind of a greenish area here. Okay, you see what I'm doing. The actual area is the black and red, because it's black because it was overlapping the blue and the yellow. So that's the actual area. The yellow is showing you that that's the top part that sticks out above. The black is the part that's down below, and the red is the stuff that's in between there. So in this case, the right Reimann sum is an overestimate, and the left Reimann sum is an underestimate. And the difference between them is this little rectangle right here, isn't it? That's the difference between the left and the right Reimann sum. And this is, so this is an example of, now of course we could do some other things. We could have also just randomly picked any one of these velocities, or to be less random, we could just pick this middle, like go right in the middle, so go 1.5 seconds into it, and pick that to be my top velocity, which might make more sense because that way I'm average. It's kind of like an average velocity. So, and we could do a rectangle that way also. So, but the basic idea is I'm drawing a rectangle to represent my total distance.